So in this section, we're looking at kind of changes of state rather than changes of temperature. And the first thing, just to clarify, that heat is involved in this as well. So basically, we saw in the first experiment that when you heat water, yes, its temperature can change. People are familiar with that. But what happened eventually was its temperature stopped changing and it started changing state. So changes of state involve heat energy either being gained, absorbed, or lost, or emitted, are the kind of more technical words, absorbed and emitted, when it changes state. And then, as we saw in that first experiment, that when it changes state, you get a flat section on the graph, which tells you that the temperature remains constant. And what's actually happening there is that the energy you're putting in is going to alter the bonds. So going from a solid to a liquid, the solid, remember, you've got these regular bonds keeping the particles pretty much fixed in position. When you change that to a liquid, you break them enough for the particles to start moving around. When you change from a liquid to a gas, then the bonds are broken completely and the particles become separate. But when that happens, there is no change in temperature. So a change in state, and I'll underline, does not involve a change in temperature. And then an equation to describe these is actually simpler than the change in temperature one, because the only thing that really affects the amount of energy required to change state is how much of the material you've got, the mass. So you don't need a change in temperature term. So EH is your heat energy, M is your mass, and L, okay, stands for specific latent heat. And I'll explain in a wee second what that means. It's measured in joules per kilogram. Now you can have specific latent heat of fusion, which means changing liquid to solid or solid to liquid, and specific latent heat of vaporization, which is liquid to gas or gas to liquid. And specific latent heat is the amount of energy required to change the state of 1 kilogram of material. And once again, just like specific heat capacity, you'll find tables of this in the data sheet. Also a reminder of the units, if you're struggling to remember them. They'll be included in that table as well. And basically then, if you know how much energy you need to change the state of 1 kilogram, if you've got 6 kilograms, you multiply it by 6. If you've got 0.2 kilograms, you multiply by 0.2. So that's where the formula comes from. We'll look at a couple of examples. Start with a simpler one. So just straightforward. Calculate the energy required to melt 5 kilograms of ice. And so, discuss in a wee second, it's important that the ice is starting at 0, so it's just at the point where you want to melt it. If it was colder than that, at -6 for instance, -20, whatever, then you would have to heat it, you'd have to change its temperature first of all to get it to 0 for the change in state to start. So standard problem solving technique, we've got the mass. We don't have L, which is what's going to be involved in this formula as soon as you've identified it's a change of state, but we can get that from a table. and we're being asked EH. So formula EH equals ml. It's 5 times 3.34 times 10 to the 5. Plug into your calculator and rounding off, you get 1.67 times 10 to the 6 joules. Example 2, and we'll deal with the idea maybe of temperature and state changing within the same problem. So calculate the energy emitted, so this is going to be something that's cooling down. So I've got 0.05 kilograms of steam at 100 degrees Celsius, but cooling to 30 degrees Celsius. So for instance, if it landed on your skin, so using this to show the idea why steam burns are much worse than normal. So we start with steam at 100 degrees Celsius. Now it can't go down to 30 because the boiling point of water is 100, which means that steam can't exist below 100. So first of all, we've got to calculate the change of state from steam at 100 to water at 100. So that's our M. It's 0.05 kilograms. We look up the value of L for the change of state, specifically in the heat of vaporization of water. I'll get used to those words: fusion for the liquid solid, vaporization for the liquid gas change. And we're going to calculate EH. Plug in our numbers, and we get 1.13 times 10 to the 5 joules. But now we need to think about the water at 100 to water at 30. There are 2 steps to this calculation. So the mass is still 0.05 kilograms. Delta T, change in temperature, well, it's going from 100 down to 30. Remember to show you're working for that. Right. And C, that we can look up, you'll sometimes see it written as 4,200, sometimes as 4,180. And once again, we're being asked EH. So this time it's a Cm delta T calculation because we're looking at changes in temperature. So that's a kind of key question when you're doing these types of examples. What's actually changing in the bit that I'm interested in? Is it a change of state or a change of temperature? And you've got 2 formulas now, one for the change of state, the ml, and the Cm delta T for the change in temperature. Plug that into our calculator. And we can see it's a much smaller number. So the change in temperature involves much less energy than changes in state, and that's quite common. So the total energy emitted is what we get when we add both of these together. And just rounding off the proper number, significant figures, 1.28 times 10 to the 5 joules. That's our final answer.